Hello and welcome back to Calculus 1. Today's section 3.6, derivatives as rate of change. We're going to talk about velocity, position, acceleration. We're going to talk about a lot of cool stuff. I already mentioned that derivative measures the change. It measures how fast change occurs as well. We'll talk about those details. I already mentioned probably that you are the tallest when you wake up in the morning for the given day, and you are the lightest in terms of the weight for the given day. So if you really want to feel good about yourself for whatever reason, you should take all the measurements as soon as you wake up, and then as you go to. So those minute changes are obviously possible to detect through mathematics, but when you see someone, it's not that they're 3 feet shorter later and 700 pounds heavier, but these changes do occur. What we're going to do now is we are going to set up a framework now where we are starting with application a little bit. We are going to apply these derivatives to a concept, and we're going to take a look first at position, velocity, and acceleration, because that's what Newton did first with derivatives, and then we're going to take a look at more of the stuff later. So as you might have seen already, is that we have mathematical functions which describe different things in nature, and we can define position function as s of t. Clearly it's going to be s because it's position, right? There is s in the word. The position function is going to be the base, right? So you have to go from, let's say, your house to RVCC, and that path is given by mathematical function, which is the function of time. We can't teleport yet, so it takes a long time for us to go from point A to point B. So there is going to be a position function, and that position function will have the initial point and the terminal point, so when you start the journey, when you end the journey, and then it's going to be evolving in time. And then we're going to say that the velocity function is change of position function, which means velocity is the derivative of position. So velocity is change in position and has the handle of v of t. And then finally, acceleration is change in velocity, which will be a of t. Now there is also one more, jerk, which is change of acceleration. You experience it every time when you either step on the brakes abruptly or you push the gas pedal, right? Your pedals, both gas and brake, are acceleration pedals. They change velocity, whether it's to positive or a negative number. So both of those pedals in a car are acceleration, and then you have a choice of pushing those pedals gently, where you don't experience jerk, or you push them abruptly and you experience jerk, whether it jerks you towards the steering wheel or buries you into the seat if you push the gas, if you really step on the gas. So we are not going to use that, but that's another layer that you can add to this. So now we also know that the change means derivative, So I can start describing this as I have the position function, then I have the velocity function, which is the derivative of position function in respect to time. And then I have the acceleration function, which is the derivative of velocity in time, which is also the second derivative of position, again in time. So acceleration is the first derivative of velocity and the second derivative of position. And you know what, since I talked about it, I'll add jerk, but we're not going to use it. Just for your personal. Nice, so acceleration, second derivative of velocity. Oops. And the third derivative of position function. So that's jerk.
So what another way to say is that Vt is equal to d over dt of p?
This one.
Yeah, like that. Another would be d over dt to p. Because a section two earlier, the...
you mean the notation d dt of velocity, right? Yeah.
Is that the same thing?
It is, because it's multiplication between the two. And you know that this one would be over 1, right? So it goes dv dt. I'll talk more about notation, especially now that we have these squares and stuff. Now let's see how much physics actually makes sense once you know some calculus, and how actually easy and cheap all of those concepts are once you know these kind of things. First of all, we're going to start by saying that you want to go from point A to point B. And let's say they're separated in miles, and it's going to take you some time t from t equals 0 to t1, which is measured in hours. Later on in mathematics, Calc 2, Calc 3, you are going to learn formulas which compute the length of the curve. So you can find how far you go by working on those integrals. What we are interested in this course is to find the velocity function and to find acceleration function, because they utilize derivatives. So now, position function is given in miles, and look at this common sense. When you take velocity into account, it is going to be the change in position over change in time. Change in position is in miles, and change in time is in hours. Now you understand why it's mile per hour. So if you haven't caught that before, your average velocity is distance over time. Distance is measured in miles, time is measured in hours, so miles per hour. And then you have your acceleration, which is change of velocity in time, which is miles per hour divided by hour, so gives you miles per hour squared. Now you're used to meters per second squared for, let's say, acceleration of gravity. Well, gravity is acceleration, right? So when you are looking at these concepts, you can understand better that if you are standing still at the location in space, you are not going to get anywhere unless you accelerate, unless you change your zero velocity. You see, you are currently sitting, well, actually, here. I'm currently standing in one position. I'm not going to get out of the classroom. I can't go back to my chair. I can't go anywhere unless I change my zero velocity state to a velocity that will allow me to change the distance that I'm, right, the position. My position is here at this point, and without me accelerating to change my zero velocity to whatever velocity, like 3 turtles per hour, I can then cover the distance. So in order for me to cover the distance, I have to change my zero velocity. Now, acceleration is in charge of changing velocity. And then as soon as the velocity has changed from 0 to 1 or 10, immediately position starts changing because velocity is introduced, and the position starts changing as a result because velocity is changing position. So technically it starts with acceleration. You are not going to get anywhere if you are at the red light. You're not going to get anywhere unless you push the gas pedal. That's what it is. So what you're doing is your zero velocity gets changed into whatever velocity when you leave that spot. So it starts from position with a zero velocity. You hit that with some acceleration, and then the velocity changes, which changes the position, and then you got somewhere. Now, the interesting situation to consider is parabolic motion. Anything that you throw, doesn't matter how heavy and what the shape, unless the shape will interfere with air resistance and everything else. Anything that you throw is going to have downward parabolic motion, negative x squared. We know that negative x squared looks like this. So whatever you throw will exhibit this motion. It doesn't matter which way you put your hand and which way and how hard you throw. It's always going to be parabolic motion. Now, you might throw straight forward and just get release here and just get this part. That's still, it's a half of a parabola, but it's still negative x squared. So now, we actually have to do some differential equations to derive this type. So we are actually going to do this problem backwards and then kind of show that what we started from is okay. But when you take Calc 2 class, we are actually going to start in section, I believe, 7-9. We are going to start from acceleration and build this formula. So here I'm going to say for parabolic motion, I have the position function in respect to time to be negative 1/2 gt squared plus v0t plus y0. Position function. I was supposed to use s. I just hate that it's s. I've been using p, right, all the time? I'm just going to keep using p then. The book is using s, so p is equal to s. They're next to each other anyway, so who cares? So this is the position function. Now, what is the derivative of this? We know that the derivative of position is going to be the velocity. The derivative here is done in t, right? So it's 2t, which cancels a half, so I have negative gt. Do we all see that? In this term, the derivative of t squared is 2t. We all cool with that? 2 kills the half. G is a constant, which we copy, so negative gt, right? Plus v0 And then y0 is a constant again, and that gives us 0 there. Does anyone recognize the formula? In physics, you've probably seen this formula as velocity final is equal to velocity initial plus acceleration times time. Or you've seen it as velocity finals minus velocity initial is acceleration times time. Depends on how, who teaches it which way. That's that formula. G is the acceleration. And then, if I take another derivative, acceleration, I just get negative g. That's negative g, acceleration, downwards, right? So we started with what we thought it was appropriate for parabolic motion, and then we worked it down all the way by taking derivatives to the point where we show that acceleration is actually acceleration of the gravity. And it's negative because it points down. Yes?
What about, like, say you throw an object, wouldn't it accelerate after it goes, because instantaneous force means that it wouldn't have the start velocity the moment it goes out of your hand?
The object cannot accelerate on its own. It has to have some way of acceleration. All of the motion that it inherits is what you gave it with the initial throw.
Yeah, I'm saying that by throwing it, you would give it acceleration and not velocity.
No, you're actually giving it velocity, not acceleration. Velocity, because as you can see, before I let the marker go, right? My hand is moving with that speed. So if you're looking at by the way, the speed is just the velocity without direction, which is to me very interesting because they say speed limit on the highway. That technically means you are supposed to go 65 miles per hour. It doesn't matter which direction, which is kind of scary. But we'll discuss those things at some other point. So speed is the same thing as velocity minus direction. So I don't care if I throw a marker that way, or that way. It's just how strong I am. So now observe this. I am not going to give any velocity, right? I'm not going to give any velocity, and when I let go, the only thing that it's going to do is it's going to be governed by the acceleration of the planet, which is gravity, right? And the marker is going to go down. Now, when I throw marker, I am giving the velocity, I am giving it the initial velocity, which is that v0 term. So as you are dissecting these equations, this term over here will make sure that the object hits the ground. It's going to fall. It's going to be attracted by the planet. This term over here governs how far technically it's going to go away from you, because it depends on velocity of your initial velocity of the throw. V0 means initial velocity. And then over here is the initial height, because it matters whether you have a 7 feet tall player playing a basketball or a 3 feet tall player playing a basketball, right? It's not going to be the same in terms of where the ball goes. So all of these terms are very important, and they all do a certain purpose. Now, when you throw an object, it inherits the speed at which you throw. So if I throw it lightly, it is going to go slow because that's all I gave from the initial throw, and still gonna hit because obeys the equation. So that one is just gonna go a little bit because I gave a little bit of the. Now observe that I'm resting my arm on the chair to have the same y0, and we know the gravity term is the same. So now if I give more velocity to it, it's gonna go further. And the only difference, because I was resting my arm constantly in the same spot, the only difference was v0 in that case. So we have the understanding of this. Now every single object behaves this way, and no matter what you throw. Now obviously if you have object that is shaped in a way where the air resistance is going to carry it further and so on, then this equation doesn't apply. You have to have different equations which will take air resistance and other things into consideration. So if I am to take a paper, right, and throw it the same spot where I had the marker with the same force, it's not going to go where the marker went because of the shape of the paper and the air and so on. But if we are in a zero gravity environment or near zero gravity environment, if I was to throw this paper, it will go the same way like the marker, right? Over here, there's just simply gravity of the planet too strong, air resistance too strong, right? So there's a lot of stuff that would impact the paper to go differently than, right? Marker is much heavier than the paper, so gravity works better on it, and then obviously, right, the shape of the paper, which allows for air to has a say in it. So guys, what are we talking about here? We're talking about throwing a ball, basketball, baseball, whatever, or throwing anything. In Calculus 3, I have a problem that utilizes these ideas, but in using different sets of equations, but utilizes this idea where I have one student riding the Ferris wheel, the other student trying to throw something, at which point you need to throw so that the one wheel turns and the parabolic motion and they hit the same point. So let's say you're trying to toss a camera or something to a friend on a Ferris wheel, right? What are the specs of the throw so that it actually just lands in the hand of the guy who's spinning? All of these calculations are possible. It is just you know, being careful of how to write equations, where they intersect, the time, and all of that kind of stuff. The independent variable for all of these problems here is time. Everything happens in time. You accelerate in time, the velocity in time, the change of position in time. So everything is in terms of time. So your graph has to have t on the x-axis. And now we can use these equations to consider the vertical throw, and we know that the object that we throw vertically up will just come back down. You are going to throw with the initial velocity v0, because if you don't use the initial velocity to beat the gravity, you let go, the object will just fall back down. Technically, to launch the rocket into space, you need to beat what we call exit velocity, right? The exit velocity is the amount of velocity, which is the thrust you need to get the object off of the surface. Oh, damn it. 4. It's too much. What happened?
I said working hard.
That's it for the week, man.
Yeah.
Yeah. Yes.
Wouldn't it just be a matter of overcoming gravity?
Yes, but it's also long way to go, and where you need to get eventually. We do not have technology to shoot anything directly to Mars. That's how pathetic we are. Mars is the closest planet, right? And we can't get there with what we have. The way to get to Mars is to slingshot around the moon.
Right.
So you have to wait for Earth, Moon, and Mars to align. You can't send anything to Mars when it's on the other side of the sun, right? So we have to wait for this perfect alignment, and you launch a rocket, and then it slingshots around the moon, and then it lands on Mars, and that's how sad we are as a species. So. Yeah. Yep. Whenever they do what?
Huh? I said we need like a space station in between Mars and.
Musk is working on it. I'm not worried. He's got the things.
No, the moon's too close. We want farther than the moon, so it can sling. Or it doesn't even. Have to sling.
What we need is a Death Star. That's what we need.
I mean, like,
Because I think that our Congress would be able to comprehend that. Right? All the other scientific marvels, they're not able cognitively to conceptualize that, like the particle accelerators and fusion reactors or anything. So everything is built outside the country because Yeah.
Particle accelerators to create.
But then maybe if the scientific community is smart enough in US to say, you know what, we're going to build a military facility in space, Death Star, I think that the Congress would just give infinite resources, and then we can just use it for science and never tell them what it's on, because they don't comprehend anyway.
I forget, but it unfortunately might violate a convention against weapons of mass destruction. They ban the use of specific kind of weapons in space, like.
Yeah, there is. Yeah, there is something like that, but. Yeah, you're right. Yeah, they'll figure out the way. But if just the military operated, it's going to work. All right, let's go back to this. So, guys, anything that I throw. So, my question is, what is the highest point that we could reach when we throw something with the initial velocity, right? What is the highest point it reaches? So, where is this max height? When does that occur? Well, max height obviously occurs at the top. And what is the feature of the object that went all the way to the top and went back down? What's happening at the top? What's happening with the object? Yes? Yes. So the velocity gets to be 0. When I throw something upward, it goes positive y-axis. So I'll say I throw it, 10 miles per hour, initial velocity up. It is going to go up, and then it's going to stop. Once the formula that we had over here, right, when this term becomes significantly large because time t is ticking forward, right, times g, when that perfectly counters the v0, the velocity of the object is going to be 0. So what happens at the top of the trip at the maximum height is that velocity is equal to 0. And then, because nothing is supporting the object, the gravity will pull on it, right? It doesn't pull, it bends the space-time, but let's just say pull. The object will fall, and it will start picking up the velocity as it goes down. Now, this is also the game of energy there, but...
What about horizontal velocity? Wouldn't it still have that even?
This is just a vertical throw. We're going to discuss the other one separately. So the vertical, we don't consider any of the horizontal. But yes, you're right. The horizontal component of the velocity is always constant. Whatever is given in the beginning will remain. So where's the maximum height? Maximum height is when the velocity is equal to 0. So you take v of t equal to 0, and we can get time t at which height is max. So that means set the velocity equation to 0. Now we're going to also connect this later with another concept. And now finally we have the parabolic motion. Whether you kick the baseball or you fire a cannon or whatever it is, we are going to have the initial velocity in this case is going to be a vector which is going to have two components to it. It is going to have the initial velocity in x direction and initial component velocity in y direction. So these are v0x and v0y. Initial components. Was it Luke? So Luke said that your vertical component is always constant. So v0x equals constant as you throw something at an angle. The so horizontal component is constant. The vertical component is the one that goes to a 0 and then starts picking up. So at this point here, your v0y is equal to 0. And the v0x is equal to constant, which is the same value for everything at the max point there. What happened? Yes, this one is x. The bottom one is constant. That one doesn't change. And the top one is constant. So now this all happens in time. So at this point, there is only a horizontal component that is shooting straight forward. And then as this object starts getting pulled down by the gravity, well, it's always pulled down by the gravity, but that's why it was slowing up initially, and then starts accelerating due to gravity, you can see that all of these other ones right there, those are all tangent lines, guys. That's all the velocities that you get as you are going towards the end over here. So these were all concepts, and you can look at this and say, well, that's physics. But actually, if you look at it, there's nothing else other than math anywhere, because we just have application. If you are a mathematician, it takes you 30 minutes to transition into any field, because everything else is applied mathematics, and then it just depends on how technical you get with terminology and specific equations. But it all starts here. So this is what Newton figured out. This is what Newton figured out, and then let's build up on it everything else after that. So now what we're going to do is we're going to take a look at the problem, which says let the position function be so and so. When does the object hit the ground? What is the maximum height that the object will reach? How fast the object is going after blah blah, and so on. So you can find all of that information, and I hope you see how important and powerful that stuff is, because you can figure out where is the rocket, where is the airplane, where is the car, where is the, as you are trying to do things in compute. Obviously, to create any kind of mechanical systems which will have these components moving. Yes?
So what's G equal to as far as value?
So gravity on Earth, on average, is said that it's 9.81 meters per second squared. That's some average. The higher up you are in the mountain, it's lower. So, top of the Mount Everest will have lesser value than this, like 9, I don't know exactly, but 9.79, let's say. And if you are very, like at the lowest point, and what's the name of the deepest trench where they buried? I'm sorry?
Mariana?
Yeah, where they put the Decepticons. Yeah. So, yeah, so Mariana Trench, yes. So the gravity there would be more than this number, right? So, but those are all slight changes, and we just saw, and in many problems they round this to 10 for ease of right. So that's in the international system of units with meters second kilogram. And we also have the imperial units, which is pretty much US and England and no one else, which is in feet and second. So that will be 32.2 feet per second squared. So those are the two values that you were looking for to compute. Now, I'm going to go pick up one of the homework problems, and then we're going to talk about other aspects of this. There's a lot of cool stuff in this section. So let me see. So here is the problem. Let's say problem 14. It's just fine. Whatever. They're all the same. So position function is given as, they call it f of t. I'm going to call it p of t. 18t minus 3t squared on 0 less than t less than 8. I will immediately tell you that this problem is not happening on Earth because our equation is 1/2 g. 1/2 g is half of 10 is 5, and we have a 3 there, right, in front of t squared. So this is not happening on Earth. This could be Mars, possibly, right? So we have this type of equation. Here are the questions. Get me the velocity equation. Get me the acceleration equation. Go. What should I do for velocity equation? Derivative. Good. What is the answer? Good. 18 minus 60. Fine. And then what's the acceleration? -6, right? So it's not -9.81 or 32.2. So this is not Earth. Great. Now I would like to know velocity after 5 seconds. Okay, so we are going to calculate v of 5. Very good. So 18 minus 6 times 5 is -12. Now, does it make sense to be -12? The velocity meaning, no, it just means going the opposite way, right? Going down. What happened? The derivative, right? First derivative, second derivative.
Well, I know how to get 18 minus 60, but where you want take the derivative again.
Take the derivative.
Oh, you did.
What's the derivative of 18?
Sure.
And what's the derivative of -60?
-50.
Good. I would like to know the max height. The max height that the object is going to reach. So how do we calculate max height? Very good. Now that's going to give us what? Is that going to give us height? No. What is that going to give us? Time at which the max height occurs. And then you have to go to position equation to find what the height is. Good. So we have 18 minus 6t equals to 0. So t is equal to 3 seconds, right? Great. So now we are going to find the p of 3, and that will tell us where the what the maximum height is. So 18 times 3 minus 3 times 3 squared. So the answer is? How do we compute this easily? You have 18 times 3 minus 9 times 3. So that's 9 times 3, which is 27. Whatever the units are, feet or second or meters. So maximum height is 27 meters, let's say. We know that the acceleration is -6 meters per second squared. We calculated that above. So these are the type of questions that you are looking at figuring out. Now, there are also a question that I could ask is, I give you the equation, and I also ask what's the initial velocity over here. I give you the equation, and I say one of the questions, what's initial velocity? What would you say?
Oh, wait.
18. Because what's the equation? -1/2 gt squared plus v0t. V0 is in front of single t. That's this term. That's v0. This is 1/2 gt. G. 1/2 g, which means -6. right? That's how I knew before I calculated anything that this was not Earth, because that number is not 5 or 16. Good. Now I would like to discuss the difference between the average velocity and instantaneous velocity, because those are two different creatures. We have, and you need to be able to distinguish between the two. So when you are going from point A to point B, you hopefully stop on the red light, on stop signs, and then you might be speeding, right? I didn't say hopefully for that one. I said you might be. But on average, you get to be going one speed from start to finish. So your speed was 0 for 30 seconds on the red light, was 0 for 3 seconds at the stop sign in your neighborhood, but then your speed was 55 or 65 or 75 on the highway, depending which road you take. So when you go from point A to point B, you can take the entire distance and take the entire time and say that the average velocity is equal to distance divided by time, which is this. But remember that now we actually have the position function to describe point A and a position function to describe point B. So what I can do is understand that this is my time 1 and time 2. So the better way to understand this would be to use the slope equation, which means position at time 2 minus position at time 1 is divided by t2 minus t1. So you have position over time, and you are calculating average velocity here. And now this is equivalent, guys, to your slope of the secant line. So we have a way to calculate average velocity. Now, Brian, how long does it take you to get to school in driving?
20 minutes.
20 minutes.
15 if
And
really.
you have 15 miles, and the distance is equal to 15 miles. Now, what I'm going to do is I'm going to set A point as a home. Well, actually, I can just use age, and I can use RVCC. Well, then I can spell home because it's also 4 letters. There we go. And I will say that you are taking 0 to 20 minutes to get there, and you're going 0 distance where the home is to 15 miles. So if I want to calculate the average speed of Brian getting to campus, it's going to be the velocity, which is right, the speed is miles per hour. But remember that the 20 minutes I need to divide by 60 to get into hours, right? So your average speed is 45 miles per hour. That's what it is. Now, 45 miles per hour, you had to go through a 25 or 30 or 35 speed limit somewhere. You had to go through a stop sign or a red light somewhere.
22, so it makes
But there's also a highway portion, right? You're on 22 or 78, which makes this an okay average overall, because you are on the red light with a 0 velocity, 0 speed for at most, let's say, 30 seconds, where you will be driving for 15 minutes at speed of 55. So that really changes the average in favor of faster speed on average. but the speedometer, as you are driving, is constantly changing values if you are pressing either of the pedals. So the speedometer that you see, the speed that you see at a speedometer is not average speed. Otherwise, it would just be at 45 all the time for this particular trip. So that one is instantaneous velocity, because as soon as you push the brakes, right, you all know that you're driving down the highway and you see behind you a car, or you see parked right in a shrub somewhere. You immediately look at the speed and you push the brakes, right, because that lowers the speed. That's instantaneous velocity, and instantaneous velocity is the derivative. That is a snapshot. So think of the photo finish for like horses racing or whatever it is. It is like a snapshot of the infinitely small interval in time, and that shows how fast you are going at that instant. And the 45 mile per hour average for Brian was over 20 minutes, right, interval. This is going to be a split second. So instantaneous velocity is the derivative. So V equals derivative of position over time. That's what it is. And we understand that as the speedometer in the car, something that measures every instant of time. So that's what we have for this. So you can actually measure the instantaneous velocity, which is what we are actually doing here when you take, right? That's negative 12 miles per hour or meters per second, whatever the units were. What did I use? Meters per second? I didn't put the unit. That's -1 or -2, depending on the problem. So negative 12 meters per second was instantaneous. And you know what? In the next instant, that number is going to be higher, right? So that's what we have. This is what we did. This is in this example, there will be this equation here, and when you plug in, this is the example of what I just talked about, right? So if you are driving from home to school from, let's say, 12 to 12:20, right? What is your velocity at 12:05? Well, that's at 5. So V of 5, it gives you that you're going -12. So that's technically what it is. So you take the derivative of the position function, an equation that you get, which is a velocity function, you got it from the derivative, and that represents instantaneous velocity. So that one will be measuring instantaneous velocity. And if you use algebra, where you have the final destination minus, so you have distance divided by time, that's average.
So the derivative is the derivative of the entire function?
Well, the derivative of the position function is velocity, right? Let's take a look at more applications. One of my favorite is, do we have business majors here? And economics and so on? Yep, so this is for you guys. In the world of business, I guess the word derivative is prohibited. So instead of using the word for derivative, the word that is used is marginal cost, marginal profit, and so on. That is the derivative of the cost equation, the profit equation, and so on. So the problem that we are going to do, I'm going to actually, this is one of the few times when I'm forced to work out whatever is given in the textbook, because there is only 1 or 2 homework exercises that you could try on your own. So if I do those in class, then you don't have any problems to practice. So I'll have to go over the example that it's given in a textbook, even though I'm fully aware that you know all the letters and you can read all of that on your own. But such is life. So for business economics applications, we have few of these concepts that are dealing with profit, revenue, cost, and we say that the cost equation is going to be given as C of x in terms of units produced. You have to understand that in order for you to operate on a business and produce some stuff, you actually have to set up the production, which costs money to set up. That's a fixed cost. You have to, there's a lot of details in all of this. So the overall cost equation is going to be the cost per unit produced, and then added to that the fixed costs. And then you have the periodic costs as well, right? The operational costs, the electricity and all of that kind of stuff. So all of that works together in a one single equation for cost. And that equation describes costs of making units. Yes?
So X is number of units produced?
Yes. So that's why I said in terms of, which is, yes, that's X. Good. So once you take business and economics courses, you will understand, and you all should take at least one of those courses to understand how the stuff works. If you are looking at the production, if you are going to make 3 of something, I hope that we will all agree that the rocket that goes and delivers stuff to space station or install satellites is pricier than the Ford Focus, right? Because Ford Focus is going to make thousands upon thousands of models and cars, and they're going to build 2 rockets, right? So you know, there is that part of the setting up the unit and custom production and so on. Also art, you know, art is expensive because it takes a long time to produce. Someone is going to paint a painting for months. So works 8 hours today on a painting, then comes back tomorrow, works another 8 hours and another 8 hours and another 8 hours. So when that painting is posted for $10,000 to be sold, well, there is another, you know, 5 or 6, and that makes $50,000-$60,000 a year, right? Depending on the quality of the work. So it's it's one made. It's not that a painter is going to has a production where you are going to. Now, obviously, with photography and other things, that's a different story, but I took the extreme example when you make a sculpture, when you make something that it's just one unit. So, of course, it's going to be very, very expensive. And then if you have a print of something, it's not going to be as expensive because you can have hundreds of copies of that. It's easier, much easier to deal with. So the cost equation is the one that you have to consider. And then you take the revenue. So profit is going to be revenue minus the cost. Revenue is all of the stuff that you sell. It's the price times X, which is number of units. So if you sell 1,000 things that cost $100, right? You have $100,000, and now you have to subtract the cost from that, which is resources, right, and labor and utility and so on. Why are the online books cheaper than the flesh and blood? There should be common sense. There is no distribution, there are no trucks, there are no warehouses, there are no people packing and stuff. It is a very simple, it's the ebook, you rent the ebook, and that's it. Why is Amazon cheaper than Best Buy? Best Buy has to pay lease on the space, 5,000 workers that are running around, right? take all of that stuff. Amazon has what? One warehouse. Well, guess what? Best Buy has to have a warehouse as well, right? So they're equal in that respect to have that kind of cost, but then Best Buy has to have much more cost. Now, I understand that there is website and security for Amazon, but Best Buy also has the website and security because they also do that stuff as well. So you see how the cost drives and changes the market. Now, you need to take these courses to understand how these things work on a much deeper level than what I'm talking about. But the cost of is a very big part. And the profit is the money that remains once you sell the product, and then you can hopefully invest most of that money into R&D, research and development, for the new model. I mean, imagine that if there was never a second edition for whatever cell phone you're using, right? We're still on Samsung 1, iPhone 1, right? Because these companies never invested in research and development, and they never created the new, right? Because the salaries for people who are developing these things come out off of that fund, right? It's a profit fund, and then they invest that money into making something new. It doesn't go all into the owners' yachts and houses. I mean, the chunk of it goes, but it goes back into R&D to make a new, better version to stay competitive on the market. And all of the companies that fail to do that, they actually become obsolete and they die. That's how it works. So you have to have a big chunk in there. So now, once you consider all of these things, let's take a look at the problem that deals with these kind of questions. So we are going to have the average cost first. So average cost is the cost, we put the bar on top, and that's the cost function divided by the number of units produced. So that's the average cost. Again, you have to understand, and you will see clearly from this example, that producing less amount of units costs more. And even if you're producing a lot of units, it's not the same amount of cost to produce the first and the 7th and the 10th and the 100th unit. Even though you are making the same unit all the time, the cost of the first unit produced is much higher than the cost of the 100th unit produced. And you're producing the same thing. It's just how the whole thing works. And you can't understand that unless you understand and see how it works with calculus, because calculus is the one that reveals that if you are making 100 markers, the first marker in cost, let's say, is $2, and the 100th marker is 80 cents. That's how it is. Now, it's the same marker, does the same thing, lasts the same time, same amount of. So that's the average cost, and then the marginal cost is the derivative of the cost function. That's simple as is. So those are the two concepts that we are working with here. Yes?
What do you mean by marginal cost?
That's the name for it. It's just the derivative that shows change in cost. And I will, when I do the example, I will explain that further. So what we have now is the cost function. I just need to find where the cost function is. So the cost function c of x is given as negative 0.02 x squared plus 50x plus 100. And we are considering making 0 to 1,000 units. So the first question is determine the two costs, the average cost and the marginal cost. So the average cost function is going to be when you divide by x everywhere. So negative 0.02x plus 50 plus 100 over x. And the marginal cost is the derivative which is simply negative 0.04x plus 50. So that would be our marginal cost. You're only taking the derivative. Obviously, the derivative of plus 100 is 0, so we don't worry about that part. So here are our two equations that we are going to use. And the first part here says, determine the average and marginal cost for the first 100 items. So I want to know how much is C of 100, C bar of 100, and C prime of 100. So we plug 100 in. We get negative 2 plus 50 plus 1. That's $49 per unit. And if I plug in 100 into the derivative, I get negative 4 plus 50, which is $46 per unit. Now, this is only one data point. I don't see anything from here. Well, actually, no, I do. The average cost per unit says it's 49 per each unit produced, but the 100th unit is 46 bucks. So you can see that if each unit costs the same amount of money to make, each one would be 49 bucks. Now the 100th unit is 46. That means that the first unit had to be much more, 26, so they can average this 49. That's like the same idea with your grades. If you have a lower grade on one of the exams, the next grade can't be 70, has to have more than 70 to compensate for the shortfalls of the one that is below 70, because you have to have 70, that's a level playing field, and then more to compensate for the other one. So over here, as I said, 49 is the average, but then 46 on the 100 units says that we are, actually it's more expensive than 49 bucks to produce first couple of units. But let's see what happens at the 900 units. So for 900 units produced, we have negative 0.02 times 900 plus 50 plus 100 over 900. So this will be negative 18 plus 50 plus, and 1 divided by 9 is 0.11111 going forever. It's a division by 9. So yeah. And then I have 30. Yep. Dollars per unit, and the derivative of 900, right, would be 0.4, so that's negative 36 plus 50 is equal to $14 per unit. So now you can compare between the different amount of units produced, and you can also compare. Well, let's take a look. So look at the average cost of making 100 units and making 900 units. See, on average, that drops from 49 to 32 per unit produced. That means that the more units I'm producing, the lesser the cost. Now, does that make sense? Why? Why would that make sense? To have, if I produce more units, is that more time, more worker salary, more, yeah? So you already paying that money, right? Like you said, a fixed cost. So let's say if you fixed cost, that's the one. 6 months, you will pay $50,000 for your company to run. You already have the machines. You don't have to, right? That's the fixed cost. You already have the machines. You don't go and set up a new machine for every single unit that you're producing. When you are starting production, why was Elon Musk from Tesla, right, bankrupt for some time, right? Had zero money because he invested all to make the factory that will make the cars, right? None of that technology existed. He couldn't utilize anyone else's technology. So he had to come up and build the factory with custom stuff in it and then start the production, which is the reason why those cars that are much simpler than the mechanical cars that we have now cost more. Because, right, Ford and all the Nissan and all the other companies, they tweak their existing production for the next model. Those are minute changes to robots and machinery in comparison to building something that doesn't exist from scratch, right? So if you are making more units, it makes sense to have less cost on average as you make more units, because machines are already in place, blueprint, design, everything is there, and you just keep the cost there is technically now raw materials, right, coming in, but you don't have to worry about setting up the production. Now look at the cost of the 900th unit in comparison to the cost of the 100th unit produced. It goes from 46 down to 14. Now this one shows how much money you are spending to produce that particular unit. So the marker number 900 that came off of the production line, so it has a serial number on it, 900, cost me 14 bucks to make, which is pretty much materials for it and, you know, a little bit over top for our, well, materials, obviously, the workers and all that. Where the 100th one was 46 bucks because I'm still paying off the machinery, setup, and everything else that is there. So you can see clearly Calculus shows over here that the more units you are producing, the better off. Now also you have to play the game of supply and demand. You have to understand the market and everything else, because if you make way too much of something and no one is buying it, then you lost money because you can't sell it. So there is a lot of different things that you have to juggle in between. You have to know your market and everything else to be able to predict how much of what you have to make. Obviously, you are looking to make a profit, to make salaries and everything else. So that's all that I would like to talk about in this particular section of the course, mainly talking about the velocity and so on, and this business application. There's another business application after this one. You guys definitely, that you have that as a major, should check it out on elasticity and so on. Read the example, again, calculus, some derivatives, and you move along. The next section is the most important and the most powerful technique to take derivatives, called the chain rule. So we're going to restart the stream after the short break and dive into the chain rule.